Welcome. And today is a great pleasure to have Maine Christos from Harvard and to be our speaker. So thank you very much.
Thanks for the introduction, and also thanks for the invitation to come and speak to you today. So my talk will be on different models for unconventional superconductivity in the moiré materials. So just to start off, I'd like to give some motivation for why we study the particular class of materials that we're studying here. So really we're thinking, I think a more accurate name is stacked van der Waals materials, because this field has expanded now, and very interesting phases have been found in both twisted and untwisted versions of these materials, where you're stacking atomically thin layers. So some material could be a semi-metal like graphene, or semiconductor like tungsten diselenide or HBN. And then they could be at some relative stacking configuration or twist angle. And this is a field that's really taken off in condensed matter physics. And I think that, at least in part, this is due to the tunability kind of intrinsic to these types of materials. So if I think about something like high temperature superconductors, where you have this phase diagram constructed as a function of, say, temperature on the y-axis and doping on the x-axis, for every individual doping data point, people have had to fabricate or grow a new sample and then characterize its properties, and that's how phase diagrams have been constructed for those materials. But for the van der Waals types of materials, you can really just control something like the doping with electric fields, and then you have all these other sort of tuning knobs available to you. So if you're stacking materials at a relative twist angle, you can obviously vary that twist angle. You can change the type of material you're stacking, the configuration, the number of materials, or the number of layers, and then you can imagine putting them in different configurations of electric and magnetic fields and getting phase diagrams as a function of all of these parameters. And so what this tuning has really allowed for is the ability to engineer these systems into the regime where strong interactions are relevant to the physics. So by strong interactions, I'm talking about the Coulomb interactions between the electrons, and many of these systems have some limit where their non-interacting spectrum shows a flat band. So if you want to study the types of phases that you get from strongly correlated physics, these materials are really a great playground to both create and explore these new phases with a high degree of control from all of these tuning knobs that you have. So the phase of matter that I'll be talking about today will be superconductivity. So just to give a lightning review, or actually, yeah. So before getting into the details, the general question that we wanted to answer with the work I'll be talking about today is, can existing experimental observations in the moiré materials that show superconductivity be used to constrain the possible pairing mechanisms? So can we take everything we know from experiments so far and use this to sort of rule out or say certain mechanisms are more likely? And then we want to kind of play the inverse game and say, given a specific pairing mechanism, can we make any predictions either on the pairing symmetry or properties of this pairing, which can then be compared to future experiments? And so to do this, I'll be studying these properties in two different systems. So one of them is twisted bilayer graphene. So I'll start off by talking about what do we know about superconductivity from the existing experiments so far. And then I'll sort of list out all the possible pairing states in this system enumerated by symmetry and discuss which of these pairing states are compatible with the experimental constraints. And then I'll talk about the mechanism. So what are the possible pairing glues at some mean field level? And in particular, I'm going to focus on superconductivity emerging from some interaction between electrons and collective bosonic modes of the system. And I'll talk maybe a little bit more about the role of IVC order, and I'll explain what IVC or intervalley coherence is later on in the talk. And then in the last part of the talk, I'll talk about a different example where I'll argue that the same kind of way of thinking about things with fluctuation-mediated superconductivity can also apply, which is the more recent experiments in twisted tungsten diselenide. So there we're going to kind of play the same game where we'll list all the possible pairing states, and then I'll discuss the pairing glues, and I'll try to argue that kind of a unifying thread among all of these systems is the presence of IVC order, And so IBC fluctuations will play a role, or I'll argue may play a role in superconductivity in this system. And we'll see an interesting role being played by the band topology. So both of these systems have turn bands, and in twisted tungsten diselenide, something we found is that there's a very interesting contribution from band topology on the energetics of superconductivity in this case. So starting off with twisted bilayer graphene. So just to give a lightning review, we're taking two sheets of graphene and then stacking them on top of each other at some relative twist angle. This twist angle breaks the translation symmetry associated with each individual sheet of graphene, but it gives rise to a translation symmetry associated with the larger moiré unit cell. And if you look at the non-interacting continuum model for this system, what you find is that at the magic angle around 1.05 degrees, the spectrum looks like this. So you see two nearly flat, nearly degenerate bands in the center of the spectrum, which are energetically separated from all of these other remote bands. And then you have these two flat bands in each graphene scale valley. So the U1 symmetry associated with conservation of valley is still a good symmetry in the moiré problem. And then you have two spin flavors. So you essentially have 8 total degrees of freedom in this system if we're zooming in on only these active bands. And when this system was first realized in 2018, this is where superconductivity was first discovered in Pablo Herrera's group. So this is a phase diagram that most people have probably seen, where at integer filling, nu equals 2 of this moiré superlattice. So if charge neutrality is nu equals 0, and we add 2 more electrons per moiré unit cell, they observe an insulating state. And then when they further dope this insulator, they see it gives way to a superconductor. So this is something that obviously inspired an outpouring of theory work to try to explain what's the mechanism for superconductivity here. I think that a lot of people were initially excited by this phase diagram where you have some insulating state which has some order, and then you dope it and find a superconductor with something kind of reminiscent of high TC. So there's been a lot of proposals trying to explain what's mediating superconductivity here. But since this initial discovery, we've also gained a lot more insight from experiments about properties of the superconductor. So what do we know so far about this state in twisted bilayer graphene? So the first thing we know about the normal state is that there's some type of symmetry breaking, which is setting in at higher temperatures, which is reducing the number of active degrees of freedom from these 8 degrees of freedom down to 4 near nu equals 2. So this could be some type of isospin polarization or some other type of symmetry breaking. But essentially what's happening is, if you imagine the chemical potential is lying sort of in the middle of this band at charge neutrality, there's some type of resetting happening at every integer filling, such that the chemical potential is always sort of in the middle of the active bands. We also know from something like measurements of the coherence length in the trilayer system that superconductivity is thought to be very strongly coupled. And also from the trilayer system, they measured the superconductor in an in-plane magnetic field, and they find it survives up to fields, I think, roughly 2 to 3 times in excess of the Pauli limit. So this is evidence for spin triplet superconductivity.
Sorry, the first point you said we know from what? The
For which?
the polarization.
We know from measurements of the inverse compressibility, for example. So they measure like effectively, like they see something that looks like you're filling like a Dirac cone at charge neutrality, and then your nu equals 1. So it's like kind of a square root behavior. It resets and then it starts like a square root again. So it's like almost like a sawtooth plot for the compressibility, and that's how people know that you're getting this resetting behavior. Right, so we know that it's likely to be spin triplet. And then we also know that it's very likely not a conventional S-wave superconductor. So there's a few examples of experiments that show this now. So I'm showing the STM group, or STM data from the Yazdani group here, where essentially what they're measuring is the density of states in the superconducting phase And they find that their data is best fit with a V-shaped curve rather than a U-shaped curve. So essentially, this is indirect evidence that the superconducting state is not fully gapped. And they find, like, I think they checked a D wave and a P wave that better agree with the data here. And then maybe more compellingly, at lower temperatures now, the stiffness has been measured, and they find linear dependence with temperature. So this is also evidence that you have some type of nodes in your superconducting state and that you can't have this conventional S-wave superconductor.
A dumb question. So
Yeah.
usually when people say spin triplet or spin singlet, they're referring, it's like a SU2 degree of freedom, like the actual spin of the thing.
Yeah,
But here, I guess the spin degree of freedom can mix with like valley, right?
Yeah.
So is this like in the spin sector, it's likely spin triplet somehow, or like if I think of it in this bigger space, is it still
yeah. So for the perspective of this talk, it depends on the type of isospin polarization. So if it's spin polarized, then it's just spin triplet, but you can have something like spin valley polarization. And then it's kind of like a triplet in that like
the spin
pseudospin degree of freedom, which would give you like a singlet triplet admixture.
I see. Okay.
But yeah.
Are you kind of admixing whether it's bi or tri-layer in some of these experiments?
Yeah, so I'm taking like the point of view that because as I'll say later, we know that the symmetry that's broken in this correlated insulator is the same in TVG and tri-layer, that the pairing state is also the same. As more kind of motivation, why is it okay to assume this? So if you look at the band structure of the tri-layer system and you look at the spectrum, essentially what you see is the same thing, but with Dirac cones, which are very dispersive, overlaid. So you'd see like an extra Dirac cone band. But for superconductivity, I mean, the relevant degrees of freedom are the ones that give you the most density of state. So you can argue, or there at least is a good argument, that the physics is the same in both cases. Okay. So these are the experimental observations that we want to be able to reproduce in any theory for superconductivity. And so the first thing we want to do is just write down what are the possible pairing states that are spin triplet in the presence of isospin polarization. So if we assume spin polarization, if it's kind of literally spin triplet, but if it's spin valley polarized, then it's triplet in the remaining valley spin locked degree of freedom. And then just ask which of these states are compatible with the observation that you can't have a conventional S-wave pairing. And then given this list of states, we want to then think about the mechanism. So we're going to enumerate as many possible pairing mechanisms as we can, and then ask which pairing glues will give us one of our compatible pairings. And the end goal is that these observations of the pairing can then indirectly give us some constraints on some more likely or less likely pairing mechanisms. Okay, so if you do the symmetry analysis and you assume some type of isospin polarization, so for concreteness, we assume spin polarization, but the same analysis goes through if it's spin valley polarization. These are all of the possible triplet states if we restrict ourselves to intervalley pairing. So this table by itself, I don't think is very illuminating, but we can start thinking about what these states are in terms of how they transform under the symmetries of the system. So the first symmetry you can think about is C3 symmetry. So threefold rotation symmetry. About the z-axis, we have states which are one-dimensional and two-dimensional EREPs under C3 symmetry. So the A1, A2, B1, B2 states are the 1D states. And then we have E1 and E2 states, of which you can form chiral and nematic combinations of these. But if we go back to this experimental observation of nodal superconductivity, something I think you could argue is that the more relevant symmetry to think about is C2Z inversion symmetry. So C2Z inversion symmetry is a symmetry which takes you from K to minus K and also flips the graphene scale valley. And the way it acts in the subspace of these two flat bands is it constrains all of these C2Z even states to be only band off diagonal. And then all of the C2Z odd states will in general contain a mixture of band off diagonal and band diagonal elements.
Sorry, what is zeta? In your,
Sorry.
you have delta k eta. What is eta?
Eta is like the valley degree of freedom. So it's like essentially like multiplying the pairing by the valley in either valley, whether it's in the k or minus k, like think like plus minus. Okay. And so why does it matter if a state is purely band off diagonal or has some band off diagonal components? To see why, say that I take the A2 state, which has some channel where it's band off diagonal, but completely momentum independent. So kind of like an S-wave pairing, but interband. And then I look at the mean field dispersion. If I just take a pairing like this, put it into a Nambu basis and calculate the mean field dispersion. And so I can assume some arbitrary dispersion for the flat bands that can have both particle hole symmetric part and a particle asymmetric part. And then I put this pairing in, and what I can see immediately from the form of this is that this expression will have zeros somewhere for a finite amount of pairing strength because it's an interband pairing. And to see concretely why this is, so imagine that I draw my bands like I would do in a Nambu Hamiltonian, where the blue bands are the upper and lower bands of the two TBG flat bands respectively. And the red bands are the minus of those bands at minus k. If I had a normal intraband S-wave superconductor, I'm pairing between states at the Fermi level. So I'm pairing between the same band, and so any S-wave pairing will immediately gap everything out and I'll have a fully gapped spectrum. But this isn't true for the interband pairing. And the reason is we're pairing between states which are away from the Fermi level. And so a finite amount of pairing strength, I'll actually have a full Fermi surface of states in my superconducting phase. So if you've heard of Bogoliubov Fermi surfaces, this is exactly the same physics, but we're getting it here without any time reversal symmetry breaking. And then in the limit where we crank the pairing up, eventually there will be a transition where the state will evolve to a fully gapped state. So this is a way to very naturally get a transition between a nodal state and a gap state where the pairing symmetry is the same on either side of the transition as a function of something like, say, interaction strength that's making your order parameter larger. So what we've learned from this analysis is that it's possible to get a nodal pairing with an S-wave channel just from these interband effects. And then if we go back and look at all of these other states in our pairing table, or table of pairings, and ask which of these are compatible with the experiment, we find that all of these states, except for this one sort of most trivial state, which has an S-wave intraband part, in general will have some regime where they're nodal, and generically there will be some type of transition from either a line node to a point node, or a line node to gapped or point node to gapped for all of these states. So if we're thinking about compatibility with experiment, really the only one we can rule out is this guy. And so even for all of these C2C odd states, which aren't purely interband, we can have a pairing state which has a sign change in the intraband channel, and then have a nodal to gap transition from this interband pairing effect. And so then the question becomes, which pairing glues have one of these nodal pairings, which isn't this B1 pairing, as a leading instability? Okay, so then we can start talking about what are the possible mechanisms. So one more conventional possibility is phonons. So you could think about the phonons that you inherit from a single layer of graphene, either optical or acoustic. Or you can think about phonons, which is called like the phazon mode, comes from the modes of the two layers shifting, and then you can come up with layer even and layer odd versions for all of these. So that's something more conventional. But since we're seeing an example here of superconductivity emerging from doping some ordered insulating state, something that's maybe well motivated to consider is fluctuations, because we know the role fluctuation mediated superconductivity has played in other materials like the cuprates or iron-based superconductors. So this is also something that can be considered. And then there's something more exotic, like skyrmion-mediated superconductivity, where you have some texture in your pseudospin vector, which carries electrical charge. And then these combine and pair to form your Cooper pairs. That's something a little more exotic. And then there's more things. So you can think about the Goldstone modes as mediating superconductivity. You can do Cohn-Lunger treatment of the Coulomb interaction. And then in models with repulsive interactions, people have numerically found different superconducting states to emerge. So there's a lot of possibilities, and this is by no means an exhaustive list. But in terms of the possibilities which are both easy to treat at a mean field level, and I think maybe more well motivated by experiments, as I'll get into later, I want to focus on just these two. So phonons and fluctuations. So why consider them together? And the reason is, from a symmetry perspective, there's not much of a meaningful difference between them. So in either case, the problem that we're studying is essentially electrons which are coupled to some collective bosonic mode. So the electrons are coupled to some boson phi, where either the symmetry of the order that we're considering fluctuations of, or the type of phonon is completely encapsulated by the symmetries of these matrix elements lambda j, which concretely involve taking some order parameter, maybe like polymatrix, like SZ could be spin fluctuations, and then you project them down into the subspace of the flat bands, and then these lambda will contain information both about the band topology and the symmetry of the bosonic mode you're considering. And then you do the usual treatment of this, where you would integrate out the bosons. This will generate a quartic potential on the electrons. And this V part of the potential contains all of the information about symmetry with the form factors. And then you can start looking for pairing instabilities from a mean field decoupling of this quartic interaction. And already, without doing any numerics, you can make some progress and say analytically what the leading instability will be if there exists an S-wave instability. So if you write the pairing in this form, where you just assume it's momentum independent, then you can write down a criteria of how this pairing must sort of commute with these matrix elements lambda for this pairing to experience an attractive interaction. So if this criteria is satisfied for an S-wave pairing, then since if an S-wave pairing and a pairing with a sign change both have an attractive interaction, we expect, given everything else to be equal, the S-wave pairing will be favored. And so what we can do now is just trying to be as agnostic as possible, just start writing down what are the possible lambdas classified by symmetry that we can consider, and what are the leading instabilities for each lambda if they have this S-wave type instability. And then if instability is not this trivial intraband S-wave state, we can say that the pairing glue is at least not incompatible with what's been seen so far in experiments. So we do the same thing where we assume the same type of flavor polarization we did for the superconductor. And then we can just start writing down symmetry classified possibilities for lambda j. So we restrict ourselves to guesses of lambda, which have a momentum independent form in the microscopic basis before we're projecting down to the flat bands. And a lot of these possibilities map onto the states which have been studied as strong coupling ground states by Ashwin Vishwanath and Mike Zalatel in the past. So what are these possibilities? So one of them is a time reversal symmetric intervalley coherent state. So what this is a state which doesn't break time reversal symmetry, but breaks the UN value symmetry. So it hybridizes the two graphene scale values of the problem. And symmetry-wise, this is indistinguishable from a type of optical phonon that you get from graphene that scatters also between the two values. You can also have time reversal breaking types of IVC states. So this would be something like it's called the KIVC in the literature. And then sublattice polarized states, which can also be even or odd under time reversal symmetry. These states in general will have a Chern number. And then you can come up with a nematic version of this intervalley coherent state, and then think of just a nematic state which doesn't break UN value symmetry, which is also equal to, so from a symmetry perspective, to this type of nematic optical phonon, which is inherited from graphene. So this is again, not an exhaustive list, but you can kind of think of the most likely candidates for symmetry breaking in the system, given what's known or been studied theoretically for the insulators. And then ask for each of these types of fluctuating orders, we can use our commutator criteria and ask if they have an S-wave instability. And most of them do. So we list these instabilities both in the microscopic basis before projecting down into the flat bands. And then also in the band basis, once we've narrowed ourselves down to just the 2 flat bands. And what we find, for example, is this KIDC state is fluctuations lead to this B1 state, which is the gapped interband state. And the same for the somatic state. So what we can say now is that since this gapped state is incompatible with what's been seen in experiments, that fluctuations of the KIDC for this E2 phonon are likely unfavorable for pairing or not contributing to the state which is being seen in experiment. So then of these remaining states, can we say something about which of them might be more or less likely? So I want to argue that a good state to consider is this TIBC state. And the reason for this is twofold. So the first is we actually know experimentally what the order is in the insulator. So we know the symmetry that's being broken near nu equals 2. So I'm showing a snippet of the data from the Yassani group where they did STM measurements and they were able to identify time reversal symmetric intervalley coherent order in the insulator. The actual state they find is more complicated than just intervalley coherent order. It also has a pneumatic component and is kind of like a spiral state in that the face of this IVC order modulates on the moiré units, the moiré scale. But if you take a 0th order approximation of this state, then it's something which is time reversal symmetric and intervalley coherent. So this is a well-motivated thing to consider. And then another reason to consider this type of boson is a different group measured in photo emission experiments, replica bands of these 2 flat bands where the energy spacing is roughly the phonon frequency of these A1, B1 optical phonons. And so it's believed that these phonons may be strongly coupled in TVG. And they only measure these replica bands when the sample is not aligned with HBN. And so HBN, which kills the superconductor, also seems to kill this coupling they see. So this is a twofold reason to kind of focus on this type of fluctuation.
Question.
Yeah.
So once you've identified a coupling that you like, you have this kind of way to classify the leading instabilities.
Yeah.
Do you have an intuition for whether this classification would, survive beyond mean fields? Can the order change or?
We don't have a way of knowing. I think like treating superconductivity beyond mean field, like beyond mean field and then beyond like Ellie Ashberg is a hard problem, and we can't really say much about that regime. Yeah.
I have another question.
Yeah.
This instability, you mentioned you were looking for S-wave instability, like that's.
Yeah.
But maybe I'm confusing things, but I thought in the like S-wave was sort of not likely in the, or is that a different S-wave?
So S-wave intergant. So if you think of like a conventional S-wave BCS superconductor, that gives you a fully gapped state. So that's not likely, or it's not compatible with what's been seen. But if you have an interband state, then the pairing won't necessarily gap out all of your states at the Fermi level. So it depends whether it's intra or interband. And so this B1 state is the representation that has this S-wave interband component, but none of these other states have an S-wave interband component, so they're all possible. Okay. So we want to focus now on this particular type of fluctuation. And we see that our commutator criteria predicts, and I should say this criteria is valid in the limit of flat bands. So it really is an approximation, but it predicts this A2 state, which is the interband pairing state, which doesn't have a sign change. So it's S-wave version of an interband pairing. And now we want to zoom in and kind of study this within a microscopic model. So to do this, we study a continuum model description of TVG, where we'll be solving the linearized gap equation at TC and the full gap equation at 0 temperature. And we add the interactions you get from IBC fluctuations, and then we tune the relative strength of these interactions with the interactions you get from pneumatic fluctuations to see the competition between different states. And what we find from the linearized gap equation, so here I'm plotting the eigenvalue we extract from that, is that the leading state indeed is this A2 state in this regime. So kind of going from here to here, here is where you have IBC fluctuations. This is where you have pneumatic fluctuations. We find the interband state is favored and then is kind of killed by the pneumatic fluctuations, which lead to this fully gapped trivial state. And so we find essentially that our commutator criteria predicted the right thing, that when you do the full mean field, you get good agreement. But the more interesting thing, I think, is in the spectrum, you get in either case. So if I take this data point here for the B1 pairing, and I take this data point here for the A2 pairing, here I'm plotting the order parameter. So this is like the sigma naught component of the pairing for the intraband pairing and for the interband pairing, and they're roughly of the same order. But if I look at the excitation spectrum, what I see for the intraband pairing is that it's fully gapped, and the gap is roughly of the same order as this order parameter version of the gap. But for the interband pairing state, even though the order parameter is large relative to the bandwidth, this state is just beginning to become fully gapped. And so if I vary the strength of the pairing potential, so this V is essentially a multiplier multiplying this choroidic potential attractive for either the A2 or B1 pairing. What I find for the A2 pairing is that for small pairing strength, you have the Liouville Fermi surfaces, and if you look at essentially the density of states, what you see is a peak at 0 voltage. And then if you keep increasing this coupling to the interactions, you undergo a transition where it becomes fairly gapped and then eventually goes to a fully gapped regime where you would measure something like Yoon experiments. And so if we compare this to what's been seen in the trilayer system, they actually see some evolution between doping nu equals 2 to nu equals 3 from a V-shaped gap to something that becomes more U-shaped. And we want to argue that you don't need two separate superconducting states to explain this, that you can have a transition where your spectral properties change and you have the same symmetry on either side of the transition due to these interband pairing effects.
In those experiments, did they see coherence peaks on top of the U in the experiments? I guess the ones you're talking about, Caltech, maybe?
Yeah.
Or does it actually flatten out? It's kind of funny that there's no.
I mean, like you can look at the. They do, but they also, I think, see some like secondary or other kind of maybe. So the high level takeaway is that for the type of pairing that's favored by these IBC fluctuations, the excitation gap is not the same as this order parameter. It's not proportional to it, and that you naturally have a nodal to gap transition as a function of these interaction parameters. And so we also did these for the other types of fluctuations we can consider. So we apply our same commutator criteria, and we compare this to what we see from solving the linearized gap equation. And effectively what we find is that the only type of fluctuation besides these pneumatic and KIBC, or that all of these types of fluctuations besides the KIBC pneumatic phonon give you some state which has a nodal regime. So basically in terms of ruling things out at a mean field level, we can really say this and this are not so compatible with experiments. So to give a summary of all of this in TVG, there's only one state, which is this trivial interband state, which is compatible with either nodes or nodal to gap transition. and that interband effects can dramatically shift your expectations for different experimental observables. So when they were fitting these DIDV curves, they were essentially taking a single band model and then just putting a P or D wave pairing on top of this. And I think what we've learned is that you really have to solve the full multiband problem, especially in the case of TPG, where you have two very energetically narrow bands, that these effects can become more important. And then we also saw that fluctuations of this TIBC order parameter very naturally lead to interband pairing. That there's a pairing channel which is sort of protected by the C2Z inversion symmetry. Yeah. So what are the remaining questions? So one thing you could ask are, what are the experimental signatures of interband pairing beyond what I've talked about with the density of states? So how would this affect what you'd measure in a derived tunneling experiments? And can you come up with different proposals for distinguishing between these pairing states? So in something like the Coopers, where they have these corner junction experiments, they can essentially do interference of the phase of the order parameter for D-wave pairing, but this question becomes complicated when you have potentially both sign changes and also these interband effects. And so thinking about how to do this, I think, is a hard but worth thinking about problem. And then the other thing is that everything I've talked about has been kind of a mean field treatment, but we know that the superconductivity is strongly coupled. And so a natural question is, how can we connect weak coupling results to a more rigorous strong coupling analysis? And then finally, I think one of the harder things to capture is that in TBG, the normal state isn't really known exactly what it looks like. So one thing is that it's renormalized by Coulomb interaction. So you're starting with these nearly flat bands, but then the Coulomb interactions will normalize them strongly in some way that what you end up at the end is not this nearly flat degenerate state you started with. And so modeling that in a controlled way, I think, is a very difficult problem. And then the other thing is, in experiments, it's believed now that there's some type of symmetry breaking remaining in your normal state. And so how can we think about superconductivity as emerging from an ordered normal state is a hard but interesting problem, I think. So now, or maybe I'll see if anyone has a question, and if not, start talking about the other experiments. Okay. So I want to talk now about superconductivity and twisted tungsten diselenide. So earlier this year, in the summer, superconductivity was observed in twisted WSE2 in Kin-Fai Box group and Corey Dean's group at Columbia. So this is the data from the Cornell group, and what they see is superconductivity at integer billion equals 1. And then as they turn on the displacement field on the y-axis, you undergo phase transition to some type of insulating state. And so this is, in the other group, it's at a slightly different filling and at a finite displacement field, but they also see some general transition from an insulating state to a superconducting state. And so a natural question is, could this insulator be somehow mediating superconductivity, or fluctuations of the insulator be mediating superconductivity in the same way we talked about for TPG? So if we want to apply the same approach, a good question is, how different is it from twisted bilayer graphene? And on its face, it seems like a pretty different system. So for one, there's strong spin orbit coupling. There's only one active band, so you just have less flavors than in TBG. There's no realistic limit or near realistic limit where the bands go exactly flat. You don't have this chiral symmetry that you do for TBG. And here the superconductivity is somehow showing up at an integer filling, and it's actually showing up shifted off of the Van Hoek singularity. So there's no kind of natural reason to think why it would be here rather than the usual picture where you dope an insulator and then see a superconductor. But there's also some similarities. So in either case, both TBG and twisted WSE2 have turn bands. And it's also very likely that in twisted WSE2 that this insulator is some type of intervalley coherent state. And so I say likely, so people have studied in Hubbard models supplemented with some topological hopping terms, and they find 120-degree IBC antiferromagnet type state. So essentially you break the U-Valley symmetry, and then the phase of that modulates in a way that triples the unit cell. And then in the Columbia experiment, they observe a peak in their longitudinal resistivity and also their Hall resistivity with magnetic field, which was interpreted as evidence for some type of Fermi surface reconstruction, possibly also compatible with this type of AFM ordering. So there's kind of good reason to think about fluctuations of an intervalley coherent order here too. But in any case, we can play the same game where we try to be agnostic about the type of fluctuations or phonons, and then just start listing the pairings and the possible fluctuations, and then try to make some predictions for each case, what you might see in experiment. So we use the symmetries of the system. So you have a UN-Valley symmetry, time reversal symmetry, C3 symmetry. But for pairing, one of the more useful symmetries is this inversion symmetry. So it's a symmetry which takes k to minus k, but the problem in this system is that it's broken by a finite displacement field. But luckily, the values of the displacement field where superconductivity is observed is relatively small. So you can kind of think of this as an approximate symmetry. You can see reflected in the band structure that turning on this finite displacement field at the level that, or at the rough value that superconductivity is seen doesn't really change that much. And so the possible pairing states, you have two one-dimensional irreducible representations under C3, one of which is even and one of which is odd under reflection symmetry. And then you have a dymatic state. And you can see that even though these were solved in like finite displacement field, the state doesn't have perfect separation between the even and odd components. So this is some superposition of an odd and even function, but it very approximately connects to, or very approximately looks like an odd state. Okay, so if those are the possible pairing states, what do we get when we think about fluctuations or phonons? So we study the same type of problem where we have electrons coupled to some fluctuating bosonic mode. And then we take Lorentzian static susceptibility of the following form. And then we just do the same thing where we solve the linearized gap equation in the presence of these fluctuations for the continuum model of twisted tungsten diselenide. And so for IBC fluctuations, what we find is that for a value of alpha, roughly 1, this A1 state wins, and it's a state which connects in the limit of zero displacement field to the odd momentum version of this state. So this is a state which we generically expect to be nodal. If we consider fluctuations of some valley polarized order, what we find is that these valley polarized fluctuations kill superconductivity. Essentially, what they want you to do is pair between states which aren't time reversal states, and so it just kills any state that has a Cooper log, essentially. And then we can also consider fluctuations of something that just doesn't break symmetry, so think something like an optical phonon. And we find is that the A1 state at finite displacement field is always the winner, but it's kind of this crossover between the momentum even and momentum odd state. So we can say that something like a phonon which has a symmetry will lead to a fully gapped state versus IBC fluctuations will lead to momentum odd state. And now we can see something interesting about the role that the fact that we're pairing these states in a trend band. Okay, so if we take this IBC order parameter and fluctuations of it, and then we vary the strength of this Lorentzian parameter alpha, so you can think about kind of physically you're tuning either closer or further away to this critical point, that for very small alpha, for when this is a narrow Lorentzian potential, the E state, the dymatic state, begins to win. And the reason for this, why this makes such a difference, essentially comes from these form factors. So these form factors for this intervalley coherent order have this form. And what you know, because these bands are turn bands, is that for every value of k, this quantity has to vanish for some q in the Brillouin zone, or you would be able to choose a continuous gauge. And so for k equals 0, we find that this q actually happens for q equals 0. And then the q vector, it shifts with k. But the effect of this is essentially to take this potential and make it look more non-local and kind of smear it out. And this smearing out somehow energetically leads to competition between this A1 and E state, where when it's more narrow, the E state wins and more smeared out favors the A1 state. But in either case, both of these states are pairings which have some sign change, and so will lead to nodal superconductivity. Okay, and then the last thing I'll talk about is what if superconductivity what if this IBC ordering happens at a finite wave vector? So something like this 120-degree antiferromagnet. In this case, we can model the scenario by having the susceptibility, which is peaked at 3 C3 related wave vectors. So something of this form. And then we solve the linear Scalab equation for essentially increasing the spectrum Q from the gamma point to the K point. So the K point corresponds to 120-degree AFM ordering. And what we find is that the leading instability in the case for this 120-degree antiferromagnet is the A1 state. So in this regime, we find the last state we considered to win, and again, it's the nodal version of this state. So the high-level conclusion is that there's competition between all these states which now have sign changes. And they all have an attractive channel and different limits for these IBC fluctuations. So the A1 state wins when the susceptibility is more flat. The E state wins when it's very sharp and peaked at 0, and then the A2 state wins when you have ordering at finite momentum. So in general, for all of these cases, IBC fluctuations generally lead to a nodal pairing, or a pairing which has a nodal regime depending on, I guess, the amount of displacement field and breaking of the symmetry between the even and odd parity pairings. And we saw that unlike in TPG, because your leading instabilities all generically have a sign change for IBC fluctuations, that there's an important role being played by band topology and the energetics, which leads to competition between the E state and the A2 state. And that valley polarized fluctuations suppress superconductivity and all the time reversal symmetric channels. So what are the sort of general conclusions for moiré superconductivity for this? So if you're thinking about fluctuation mediated superconductivity, I think this is maybe one of the more likely pairing mechanisms, and you can very naturally capture it with these spin fermion type models, where you just couple the electrons to fluctuations of the boson. And what we've seen from this is that, especially for the case of TVG, when people talk about is it phonon mediated or fluctuation mediated or electronic correlations, that these things can act constructively and that they can both contribute to a certain pairing channel, and it doesn't have to be this is like the mechanism or not. It can be more of a constructive versus destructive interference way of thinking of things. And the other thing I want to point out is the ubiquity of IBC fluctuations in these moiré systems. So a lot of examples of these systems is either experimentally known or theoretically suggested that there could be some type of IBC ordering in the phases proximate to all of these superconducting states. And I think we're thinking about whether or not you think fluctuations of the IBC are mediating things or not. The role of IBC ordering in the normal state and the effect of superconductivity emerging from this sort of state. And then the last thing I'll mention is that you can try to apply this approach to some new emerging systems. So chiral superconductivity has recently been observed in rhombohedral stacked tetralayer graphene. So something that we're looking at now is applying the same approach of fluctuation mediated superconductivity there. In that case, you can imagine that you get even more exotic states. So once time reversal symmetry is broken, things like FFLO type states are on the table and finite Q pairing and all of this. And then another direction I think that's very interesting is thinking about the type of states you get if you're pairing near one of these observed fractional quantum anomalous Hall insulators. So yeah, so with that, I should thank my collaborators. So this work was done with my advisor, Suvir Sachdev at Harvard, and for the interband pairing work with Matthias Schur, who's currently professor at the University of Stuttgart. And then the work on twisted WSE2 was also done with Pietro, who's currently a postdoc at Harvard. And yeah, so with that, thanks for your attention, and I'll take any questions.
Can you speculate about why it's been so hard to get the TMDs, these transition multi-chalcogenides, to be superconductors? People tried until last summer. With no
Yeah.
successes in spin orbit or other things.
I mean, I don't know of a. I actually am not sure why it was so hard. I mean, it was proposed kind of a while back that they would have these flat bands, which then give you the favorable conditions for superconductivity if you have a high DOS, but I don't have any intuition beyond that why it was so difficult.
How about just making a prediction, put it out there, since all the experimentalists are trying like crazy to make superconductivity? Would you find another material that would?
I guess like it's not so clear to me, like the way people kind of predict the material in which something will show up. For superconductivity especially, I think like the only thing you can really say is like more density of states helps. And then these other things which come from symmetry breaking come from factors that it's just interactions and you don't really know what you'll get. So yeah, for the superconducting phase, I'm not really sure.
How much is known about the normal states in these?
Yeah, in twisted tungsten diselenide, I don't think that much yet. In TBG, so I think it's debatable the extent to which there's ordering in the normal state, but there's evidence that there's some amount of ordering. So there's like this plot in the Yazdani group paper where they show the strength of the IBC order parameter as a function of doping. And it drops off as you dope away from nu equals 2, but it doesn't seem to go exactly to 0. And then they've also taken STM data at like nu equals 2.5, 2 point whatever. And you very clearly see like IBC ordering there. So I think it's clear that something is there, but whether it's like the same order as the insulator and how strong that order is, I think is up for debate.
Sorry, this is another dumb question. When you say the parent is mediated by some fluctuations, it's fluctuation of some like order parameter?
Yeah.
Like, and so do you assume this thing is near some critical point or?
Yeah. So you're assuming that you're near the critical point and the order hasn't condensed yet, and then you're considering fluctuations of this order parameter that is condensed in the insulator and not condensed once you dope. And so you could think about being in the ordered phase and also having the same fluctuations. But that would be like a different problem.
But what's like the order parameter that's there in the
In experiments or?
yeah, or in these systems?
Yeah, so in TBG, it's some type of intervalley coherent order. So the name of the order is this like IKS state. So it stands for incommensurate Kekulé spiral. So it's essentially an IBC state where the phase of the IBC modulates on the moiré scale. So it's like a spiral state on the moiré scale, but a Kekulé state on the graphene scale. And then it also has some like intrinsically pneumatic component. It's like a pretty complicated order parameter actually. But the high level point is that it's time reversal symmetric and intervalley coherent and also pneumatic.
So from a symmetry perspective, this order parameter is the same as phonons?
So there's a part of this order parameter which is the same as phonons. So there's a time reversal intervalley coherent part of that order parameter, which is very complicated. In low strain samples, they see something that they argue looks more directly like actual TIBC. So in typical strain samples, it's something that has like a TIBC component. And then in low strain samples, it's something that is more exactly IBC without these other pneumatic and translation symmetry breaking parts.
Any other questions? If no further questions, let's thank Maine again.